Hello, this is now a video of Chapter 9, Section 3, which deals with two proportion z-tests. And so we're going to do a couple of examples of that. And so here we go. So the first context here says a social worker wishes to see if there's a difference in the proportions, plural, okay, of the adults in Morgan County and the adults in Limestone County that are college graduates. The worker takes an SRS of 200 adults in Morgan County and finds that 67 are college graduates. Takes another SRS of 250 adults in Limestone County and finds that 62 of them are college graduates. Perform a test of significance to see if there is a difference in the population proportions. So I like looking at the proportions here. So the proportion for Morgan County, so our p-hat for Morgan County is equal to 67 successes out of 200, and that is equal to 0.335, okay? And then our sample value, our p-hat for Limestone County is equal to 62 out of 250, and that's equal to 0.248. So in our sample, in our samples, you know, the Morgan County was more than Limestone County, 33.5% to 24.8%. But the question is that difference statistically significant, or is it plausible that the two population values are in essence the same? All right, so we're asked to perform a test of significance, otherwise known as a hypothesis test. And anytime that happens, we have to do the THAME acronym. So in this case, we've got two populations here, and we've got two samples. So our type of inference, first of all, we are going to call this a two proportion z-test. Sometimes you'll see that called a two sample z-test for the difference in proportions. But anyway, so there you go. If you forget that name, it's on your calculator. Then the H, as we discussed last section, is you have to write your hypotheses. Okay. Now, your null hypothesis, you know, last section was just P is equal to something. Well, now the null hypothesis is just that the two population proportions are the same, is that P sub M is equal to P sub L. There's no difference in the population proportions. There's certainly difference in the sample proportions in the p-hats, but the null hypothesis is there's no difference. The alternative is what you suspect might be true. Do we suspect that Morgan County is more than Limestone County or vice versa? It doesn't say that up here. It just says, is there a difference? And so that means it is not equal to. So this would be a two-sided test, okay? The other way of writing this that you will see pretty frequently is they will subtract P sub L from both sides, and it would just be that P sub M minus P sub L is equal to 0, okay? That the difference is 0, and that the alternative then would just be P sub M minus P sub L is not equal to 0. That's just subtracting P sub L from both sides. So you can do it either way. You need to recognize both ways. And of course, whenever you write any sort of variable like this, make sure and define your variables. So P sub M is equal to the proportion of all the adults in Morgan County that are college graduates. Okay, and then P sub L, and it's perfectly fine to use ditto marks, the proportion of all the adults in Limestone County that are college graduates. So that works right there. So that's your hypotheses. Okay, and so anytime you do these two proportion z-tests, it's always going to be the two proportions are equal. Okay, like that. All right, there we go. So then our assumptions. Of course, this is really similar to the last chapter when we did our two proportion assumptions. It is now I sin. Okay, if it's just one proportion, it'd be sin, but it's I sin. In other words, they had to be independent random samples. And so what we would say is this, very similar to last chapter. We have SRSs right there, it says SRSs. So it says SRSs, plural, okay, please put plural. SRSs were taken. Of course, it could say random samples were taken, and that's fine. It says, so thus independent independent, random condition is met. So hopefully you're getting used to these conditions or these assumptions, okay? So there we go. And then the other aspect of the word independence is that our sample sizes can't be more than 10% of our population sizes. So what we'll say here is we just multiply both these numbers times 10. We would say 2,000, okay? We would say there must be at least 2,000 adults in Morgan County. And 10 times that, so that'd be 2,500. 2,500 adults in Limestone County. For little n's, our little n's, plural, less than or equal to 0.1 times our big N's. Okay, that ensures, if that's true, that ensures we can use the formula for the standard error. Please know that fact, okay? Please know the why behind these things. The randomness prevents bias. This ensures that we can use the formula for the standard error. And then lastly, normality. So normality, n times p and n times 1 minus p had to be greater than 10. Now here's something that's a little new. All right, so we've got n times p and n times 1 minus p had to be greater than or equal to 10. Now, you know, last chapter we used the p hats there, and then the previous section we used p naught. Now, this is what we're going to do. We're going to use what is known as a combined p hat. Okay, we operate this whole test assuming the null is true. The whole logic of this test, if we assume the null is true, if we assume there's no difference in Limestone and in Morgan County, okay, what's the probability we would get sample values this different? Okay, that's the logic of this test. And so to use this, so we are going to combine our p hats into a larger sample that gives us a larger sample size, which creates less variability. So this is what is known as a combined p hat that we're going to use in this step. So our p hat combined, and sometimes you'll see it called pooled, and this is on your formula sheet. So if you turn to page 2 of your formula sheet in the standard error, so we're going to use this in our formula for our standard error. It's going to be that, but that's p hat combined. It just means add up your x's and add up your n's. Combine your two samples in essence. And so this would be equal to, 67 successes in the first sample plus 62 over 200 plus 250, like that. And so that is equal to 0.286 repeating, 0.286 repeating, like that. And so that is the value we're going to use there. So this is what is known as the combined p hat, like that. And we got to do that for both samples, by the way. So so we go 200 times 0.286 repeating. And when we do that, we would get 57.3 repeating. We go 200 times 1 minus that, which is 0.713 repeating. And so that is equal to 142.6 repeating. Then we do it with the sample size of 250. So we go 250 times 0.286 repeating. And so that is equal to 71.6 repeating. And then lastly, the 250 times 0.713 repeating. And that is equal to 178.3 repeating. We say they are all, and I would, by the way, I would show this whole thing. I would show that you don't have to put the letters, but you have to put those numbers, and I would certainly show that you've calculated the p hat combined. I'd certainly show that. And so, but you have to say, okay, you can't just write the numbers. You got to say this. Thus, normality is met. Thus, normality is met. There you go. And that's the most involved part. Certainly your assumptions, your conditions, your sinning, but that's the way you do it. Okay, so there you go. So now we'll do our mechanics. So for our mechanics, similar to the last section, so we need a test stat, we need a test stat, and we need a p-value. Okay, and we can use our calculator. I'm going to show you in a minute how to do it by hand, and you need to understand that, but more importantly, you got to be able to do the assumptions and the ending. So let's just use our calculator. So you can always use your calculator. So here we go. So we shall go stat, we shall go test, and we go down to option 6, 2 proportion z-test, right there. Now, if you forget the name, there it is. So at the very beginning, you can just copy it off there and put it there. So that would give you the copy, that would give you the credit for type. All right, so we hit enter. And so our samples are 67 out of 200. So I go 67 out of 200. Please don't put your p hat there. Put your x and your n for both of them. Don't put 0.335 there. All right, so, and then our second, so it'd be 62 out of 250. 62 out of 250. So like that. Our alternative is not equal to, so we put not equal to there. And we go calculate, and there is our test statistic p-value. Right there, those two numbers there. Notice it gives you, by the way, your p-hat for both of them, and it gives your combined p-hat right there. It calculates that for you. So you can do all that to show your work up there if you like. So our z is 2.02. So our z is equal to about 2.028, we shall say. And then our p-value, and please write p-value, don't just write p, is equal to 0.04256. Okay? So there you go. And so that is your test statistic p-value. You have to write both those numbers down. And lastly, the ending. So the ending, we're going to say this. We're going to properly draw a proper conclusion with our p-value, which we've done for a couple sections now. We have to compare this with our alpha. So you look up here. Did they give you an alpha? No, they didn't. Okay. Alpha is a significance level that's given to you. If it's not given to you, use 0.05. So we'll say this p-value, and write what it is, 0.04256, is less than 0.05. So what do we do when the p-value is low? We reject the hoe. So I reject the null hypothesis. You could write it just like that. And then you would say, we have convincing evidence that, and you restate the alternative. Okay. Now, for the sake of time here, I'm just going to say we have convincing evidence that P sub m is not equal to P sub L. That P sub m is not equal to P sub L, and say as defined above. Okay. Technically, you're supposed to write them out again. Anytime I've ever been a part of a rubric on this is that you get full credit for this, but they want you to write it out again. And I think it's kind of silly, but so I would go ahead and write it again, but this would give you full credit. And when you do it in my class, I'll give you full credit for saying that. So the p-value is below 0.05. So I reject and all, have convincing evidence that, and then you restate the alternative. Okay. Now, if the p-value is above 0.05 or above your stated alpha, you would say, I do not reject the null. I do not have convincing evidence that, and you restate the alternative. So there you go. All right. So that's how you do it. That is a two-proportion z-test. I want to show you how to do the test stats p-value calculation by hand, okay? Because you do sort of need to understand that. So the formula for your test stat, okay, your z test stat, so your test stat. So here's your formula for your test stat. Z is equal to, now any test stat follows this in general formula, statistic minus parameter over standard error, where our statistic here is the difference in two stats. It's the difference between these two guys, okay? The difference between that minus that, okay? The parameter is the difference in the parameter, is the population values, which would be the difference between P sub m and P sub L. But we're assuming the null hypothesis is true, that's 0. So we're going to put 0 there. So in other words, the numerator just becomes, P hat sub m minus P hat sub L minus 0. Okay. The standard error of the statistic. Okay. There it is. When we assume that P sub 1 and P sub 2 are equal, okay, when we assume that, which we're assuming that in a test, in the logic of the test, here's the formula. We use our P hat combined. We plug it right into there. Plug it right into that formula there. And so that's what I'm going to do. So my z test stat is equal to the difference in these two guys, 0.335 minus 0.248 over the square root of, and going back to that formula, okay, so this would be 0.286 repeating times 0.713 repeating times, and then 1 over 200, my first sample size, plus 1 over the second sample size, like that. And when you do that, you would get the test stat, which would be, so with this, the numerator ends up being, by the way, 0.087, and the denominator, that square root thing, is 0.0429, and that equals to your test stat, which is like 2. So it equals, what did my test stat equal? So yeah, 2.028, like that, okay? So that's how you find your test stat. There you go. Now to find your p-value, we're going to use normal CDF, just like we did in chapter 7. So we would say this, all right, assuming the null is true, assuming the true difference is 0, that means the standard deviation, I mean the sampling distribution of all of our sample differences, if we took many sample differences like we did in chapter 7, it'd be centered at 0. Now our difference in our sample, so our sample difference is going to be 0.335 minus 0.248, and that is equal to 0.087. So it's over here at 0.087. What's the probability I'm going to get that more unusual outside of it? Okay. Now this is a two-sided test. So we're going to have two tails in this thing. It's not just that big or bigger, but it's also the negative value. It's just, in essence, it's that distance from the center or more or further away. And so we'll do normal CDF with that. And so we would say to find that p-value, so normal CDF, and so that's 0.087 to infinity, a mean of 0. There's our standard deviation, which that's our standard error right there, our formula for the standard error. And so that is that. So we get that, boom. And so that is it for one tail. So one tail is 0.02128. And so we have to we got to have both tails because it's a two-sided test. So we just say times 2, and it gives us our p-value. So I realize that's sort of complicated. That is not emphasized in AP Stats at all. What is emphasized is drawing a proper conclusion with your p-value, being able to do your assumptions, being able to write the proper hypotheses. So there you go. All right, then the next thing. So the next thing asks us to do this, create a 95% confidence interval with the data above and comment on the connection between the interval and the p-value of the test. So we want to make a confidence interval for the true difference for P sub M minus P sub L, okay? We want to estimate that. Now our estimate we got is 0.087, that's the difference there. So, but let's make an interval around that will be the plausible values for the difference. So let's make our interval just like what we did in chapter 8. So you remember we went stat, we went test, and we went down to option B, make our two proportions the interval, hit enter, and then look, the calculator automatically entered my data for me because it knew I was going to make this connection. It said 95% confidence. So there's our interval. So our 95% confidence interval is 0.00247 and then 0.17153. Those are the plausible values at this level for this difference. Okay. So the connection between the p-value in this is the fact that 0 is not in this interval. See, the null hypothesis value is 0. So what we were testing is it plausible that this difference is 0? That's what we're testing. Is it plausible that the difference is 0? 0 is not in the interval, so it's not a plausible value for the difference and should be rejected. And that's exactly what our p-value said to do. So you would say this, 0 is not inside this interval, so it is not a plausible value for the true difference. And should be rejected at this confidence level. In other words, 95%. Okay? The low p-value, which is less than 0.05 also tells us to reject the null hypothesis of P sub m minus P sub L is equal to 0. Okay, so that's the connection. Of course, we talked about that in the last section, but the big deal in regards to these intervals really is with the two sample intervals, two proportion intervals, if 0 is in the interval. If 0 is not in the interval, it's to be rejected. If it was inside the interval, you would say, well, it's a plausible value for the difference. So P sub m is plausibly equal to P sub L. And so we shouldn't reject it in favor of the alternative. All right, so there you go. Now, this problem is a really similar problem, but it has sort of a little bit of a kind of a different little twist to us that, and this happened to us earlier in the year as well. So let's see if you can figure this out. A doctor wishes to see if a new drug in the market is better than the old drug he uses to treat foot pain. He has 100 people with foot pain that have been volunteered to be in the study. Volunteered. He did not randomly select them. So we cannot generalize about a larger population. We have to generalize only about people like these. That's the big difference. Please understand that. All right, so he randomly assigns. He didn't randomly select them. He randomly assigned them. In other words, we got an experiment here. All right, 50 of the people into a group that receives the new drug, while the other 50 get the old drug. In the new drug group, 80% reported significant improvement in their foot pain. In the old drug group, 70% reported significant improvement in their foot pain. Perform a test of significance, see if the new drug works better than the old drug. Well, when you look at it, first of all, our p hat for our new drug is 80%, 0.8. And the p hat for our old drug is 70%, so it's 0.7. So it appears to work better, but the big question is it statistically significantly better? Or is this difference plausible due to sampling variability? So that's what we're going to find out in regards to this test. So we're asked to perform a test of significance, otherwise known as a hypothesis test. So the type of inference we must say, we got to do the same acronym. And this is a two proportion z-test. Two proportion z-test. Like that. Okay, and so our hypotheses, okay, the null hypothesis is going to be, there's no difference between the population values, is that P sub n is equal to P sub L. Don't put p hats there, okay? The alternative, now it clearly said that the new drug, we want to test to see if it worked, the new drug works better. Well, if the new drug works better, then, P is the proportion that, is randomly assigned 50 new drug, significant improvement. We would expect more improvement if it works better. So this would be bigger than P sub L, okay? And so there's our hypotheses. Whenever you write your parameters like this, you must define them. So P sub n is equal to the proportion of patients like these. Now, whenever you don't have random selection, that's the difference between this problem and the last problem we did. We can only generalize about patients like these. The proportion of patients like these that have improved foot pain with the new drug. Okay, and then P sub O is, and you can use ditto marks, portion of patients like these that have improved foot pain with the old drug. So clearly define your parameters there. All right, so we got the hypotheses now. Your assumptions, very similar to what we had before, otherwise known as your conditions. But it's all right. This is what's different. Don't say they were randomly selected. Don't say they're SRSs. Say what it says. They were randomly assigned, or in other words, randomly allocated. It says they were randomly assigned two groups So independent random condition is met for patients like these. We have to say for patient like these because they were not randomly selected. They were randomly assigned. Now, the fact that they were randomly assigned in an experiment allows us to draw the conclusion that there could be a cause and effect relationship going on here. And it's not just correlated, okay, as we talked about earlier in the year. So our random conditions are met because they're randomly assigned, okay, so that's important. We don't have to check for the other aspect of the word independence, okay? In other words, a population size being at least 10 times the sample size, because we don't have a larger population, so to speak, okay? They weren't randomly selected. So you don't have to check that condition if you don't have random selection. So say you don't have to check that our little n's are less than or equal to 0.1 times our big N's because there's no random selection. So that's that. And then lastly, normality, similar to what we did before. And so in this case, all right, so normality, all right, our combined p hat. So that is going to be equal to 40 plus 35 over 50 plus 50. Okay, those are just our number of successes and our total size there. So that's equal to 75 over 100. So our combined p hat is 0.75. So to check for normality, we'll say n, so it would be 50 times 0.75, and that's equal to 37.5. And then 50 times 1 minus that, 0.25, and that is equal to 12.5. They're greater than or equal to 10, so we say thus normality is met. So we'd say thus normality is met. There you go. Certainly the most involved part of it is the conditions, is the assumptions. Now we do our mechanics, which is our test stat. So our mechanics, our test stat, and our p-value. And I'm not going to do these by hand. I'll just use the calculator because that's what you can do. And so here we go. And so we would say stat tests, and this would be a 2 proportion z-test. So the first group had, so now, okay, how did I should have, I meant to do this up here. So once again, there's 3 numbers you need. So the first group had 80% successes out of 50. So you go 0.8 times that to be 40. So that's our first X. And then our second X, okay, we had a group size of 50. We had 70% successes. So 0.7, times that is 35. Okay, so those are our X values for our 2 samples, which is why I put those there. So hopefully that didn't confuse you. So 40 and 35 are our number of successes. And so on the first group, we had 40 successes out of 50 trials. And then in the second group, we had 35 successes out of 50 trials. And so our alternative is greater than, so it's a one-sided test greater than. And so then we go calculate. And so there's our test stat p-value. So our z-test stat, so is z, which is 1.1547. And our p-value is equal to 0.1241, like that. And so there we go. So there's our test stat p-value. Now we have to make a decision with our p-value. Our ending is our conclusion with our p-value, making a decision. And once again, we are not given an alpha here. An alpha is the value that the p-value is below that alpha, you reject null. So we use 0.05. And so we would say this p-value, and say what it is, 0.1241, is greater than 0.05. So if the p-value is low, you reject the hoe. If not, you fail to reject the hoe. So I fail to reject the null hypothesis. Thus, I do not have convincing evidence that, and then you restate the alternative, that P sub n is greater than P sub O. P sub n is greater than P sub O, as defined above. Now, once again, on the exam, this would probably give you full credit to say as defined above. They want you to write it twice, which I think is stupid. But, and so I'll give you full credit in my crafts if you just said that. Any rubric I've ever seen gives you full credit for that. But some of the gurus say, no, have them rewrite it again. So I go ahead and rewrite piece of N is the proportion of all patients like these that have improved pain with the new drug and so forth. And let's see, did it ask us anything else? No, that's it. Okay, great. So thank you for watching this video. I wish you much success, 2-proportion Z-test. If you have any questions, please let me know.